All right. In this video, this is completely optional. I'm going to show you a rather sophisticated way to define determinants. And this is a way that if you were to pursue math, say in graduate school, we would learn how to take determinants in a very abstract way, but in a way that's very sort of satisfying. And so let's start with two examples. So I have two determinants here. So let's just calculate them using the methods that we've learned. So this is going to be 14 minus 12. That's 2. And then this determinant down here, let's get some practice. Let's expand. I don't know. Let's expand across this first row. And so what that's going to mean, we're going to do 0, 1, and 2. We're going to put in our signs. So we're going to get a plus, 0, negative, and minus. And then we're going to put in those smaller determinants here of those cofactor matrices. So the 0, it doesn't really matter because it's going to get multiplied by 0. This 1, well, its cofactor matrix is going to be the pieces that aren't in the row and column defined by 1. So we'll cross off that. We're going to get 3, 2, 4, 1. And then now, if I do the last one, let's see what the last one's going to be. If I cross those off, I'm going to get 3, 3 on the diagonal, and then 4 and 0 on the other terms. And so once I calculate this, it's not so bad. I get negative, let's see, that'll be 3 minus 8, so that's negative 5, plus, and that's going to be 9. So I'll get 18. And so at the end of the day, I get 23 is my final number. Okay? So as we've said in class, one way to define these is to think about the area or volume of the parallelogram or parallelepiped that would be spanned by the columns of this matrix. Right? And so one thing we can think about is we can think about these two column vectors, 2, 3, and 4, 7. Or down here, we can think about these three column vectors, 0, 3, 4, 1, 0, 3, 2, 2, 1. And so what I'm going to do now is we're going to enter kind of a bizarro universe. It can either be a kind of a, maybe it's a nightmare world where kind of weird things are true. But I want to enter a universe where we have a way of multiplying things. And so I want to say where we have a way to multiply vectors. Right? And it's not what you think. I promise it's not what you think if you've seen a way to multiply vectors before. And the only rule I'm going to say that we have is that if I multiply any vector by itself, so if I take the vector times itself, it's going to be 0. Right? So what if I lived in a world where that were true? Right? Remember, it's a vector times itself. This is a very strange thing, right? First of all, let's just kind of be clear. Like, that's not a behavior that we see, anywhere else, right? What's 4 times 4? In our life, that's 16. That's not 0, right? Normally, when we multiply something by itself, it is never 0. But what if we change the rules of math and we said, hey, let's try to live in a universe where if I multiply anything by itself, I'm going to get 0. And so let me write that again. Any vector times itself is going to be 0. Now, I notice I've changed the symbol for multiplication here, right? Because this is such a weird definition of multiplication, I don't want to get us confused with other symbols. So I'm going to use this bracket notation. And note what this says. It says any vector times itself would be 0. And so, for instance, what that would say is if I take, this vector, and I multiply it by itself, well, I've just told you I want that to be 0. Now, what if we change it? What if we change it from, the same vector to something different? Well, we have no clue, right? All I told you was that if we take a vector times itself, not times a different vector, but times itself, it's going to be 0. So let's explore the implications of that. Let's see what we can do. Okay. So let's see what we could do. Well, let's try an experiment. what happens if I wanted to figure out what happens if I take two different vectors? And I want to know, well, Adam, if you've told me that if I multiply v by itself, I get 0. And if you multiply w by itself, you get 0. But what happens if you multiply v times w? Well, let me show you a cool trick. So what I'm going to do is I'm going to say any vector times itself has got to be 0. Let's do v plus w times itself. Right? That has to be 0. We agreed that any vector times itself had to be 0. Doesn't have to be called v, doesn't have to be called w. As long as it's the same vector, it's supposed to be 0. Right? So let's expand this out. Let's imagine, too, that multiplication is distributive. So this is going to say v times v plus w times v. Let me stop writing the arrows. This be a little bit easier. Plus, okay, that was those two directions. So now I'm going to do plus v times w plus w times w. Okay. So if we expand that using the distributive rule, we should get this equation. And what do we know? Well, we know that w times w is 0, and v times v is 0. And so we must have that whatever w times v is, plus, okay, well, these look a little bit different. We're not sure multiplication is commutative, right? We've seen examples with matrices where that wasn't true. So let's continue exploring in this bizarro universe. In this bizarro universe, what seems to be true is that if I take any vector and I multiply it by another vector, the order matters. That if I multiply if I do it in one way, I get the opposite of doing it in the other way. So now I have this is kind of like an anti-commutativity. So again, in this strange world that you're probably wondering, why on earth is he talking about this? And if you don't think this is cool, please stop watching the video, because it's only going to get weirder. But if we live in a universe where we decide that we want any vector times itself to be 0, you may say, well, why on earth would we ever want to do that? Well, you'll see something really cool that's going to happen. But if that's true, and we have this distributive property, it's going to be true that things anti-commute. So that when we switch the order of multiplication, it's actually going to introduce a minus sign. So if you are a physics student, you may have heard about kind of, super structures or something like that, where you get this anti-commutativity. This is kind of where that behavior is coming from. And so now, let's put it to use. So now what I want us to do is I want us to go back to this determinant problem. Right? But instead of, we worked it out and we got that the answer was 2. And instead, what I want us to do is I want us to just take these two vectors, 2, 3, and 4, 7, and I want us to multiply them together. And you're probably saying, well, Adam, you haven't told us how to multiply, right? You've only kind of done some sort of weird, theoretical properties. And I say, you're absolutely right. So let me help you out. So let's take this vector and let's rewrite it. This is 2 times e1 plus 3 times e2, right? The first coordinate is 2, the second coordinate is 3. And let's multiply that. Okay, well, this is going to be 4e1 plus 7e2. Okay. All right, Adam, you still haven't told us, how this multiplication goes, but at least I can maybe simplify. So now I'm going to FOIL it out. I get 8e1 wedge e1. This is called a wedge operation. Plus 12e2 wedge e1 plus 14 e1 wedge e2 and 21 e2 wedge e2. Okay, big deal. We've made it way more complicated. Oh, but wait a minute. You said you wanted any vector times itself to be 0. Okay, I'll take your word for it. I guess those are going to be 0. And so now we have 12 e2 e1 plus 14 E1 E2. Oh, so weird, so cool. I remember you just told me that I could swap the order. E2 wedge E1 is the same as E1 wedge E2 if I put a minus sign in front of it. There's that weird anti-commutativity. Oh my gosh. Now I have two like terms. Now I get, oh my gosh, I get 2. I get 2 times E1 wedge E2. And it is no coincidence that that 2, which remember we got from 14 minus 12, that's exactly 14 minus 12. So this weird, bizarro universe where we want things to square, if we multiply something by itself, we want it to give us 0, that's actually, for some reason, calculating determinants, which is somehow calculating area and volume. Let's see if it works. Let's try another example. So down here we had this determinant. This was supposed to be 23. Okay, well, let's see what it works. So we're supposed to take these 3 vectors. So let's take the first vector. That's going to be 0e1 plus 3e2 plus 4e3. Okay, that's that first column. And according to what we did before, it looks like we're just going to take the 3 columns and wedge them together using this weird wedge operation. So I hope I don't make a mistake. Right, and now we get, oh my gosh, 2e1 plus 2e2 plus e3. All right. So I've got a lot of foiling to do, right? And so I'm gonna do it. But first things first, I'm gonna get rid of this 0e1. That is completely not gonna help me. Right? And I'm also getting rid of the 0e2. Okay. And so here I go. Let's try it. Let's see what's going to happen. So if I multiply it through, I'm going to get E2E1. Okay, that's that one. This one's going to be 9, E2, E3. And then I need to do the other 2 foils. So this is going to be plus 4, E3, E1. And then 12, E3, wedge E3. I'm going to copy down this expression. And I'm going to simplify a little bit. Right? I'm going to simplify. And I'm going to say, you know what? Let's get everything in order. I don't like the numbers being in backwards. Let's make this an E1, E2. Switch it around. This one's already in order, 2 and 3. Let's flip this one around. So it's going to be E1, wedge E3, and this one is 0, because anything wedge itself is equal to 0. Okay. And so now, I have this, and now, oh my gosh, okay, so now we're going to have to do a bunch of stuff. Okay. But let me show you a way that we can kind of save ourselves some marks. Let me just show you a couple products. So for instance, this product here is going to be an E1, wedge E2, wedge E1. All right, it's going to be -6 times that. And if I were to simplify that, well, I can switch the order of these two. Remember, E2 wedge E1 is going to be negative E1 wedge E2. So I could kind of switch those around if you wanted to. In fact, I'll pull that negative out front and just get a +6. And now I look at this and I say, well, wait a minute. Now I'm going to have E1 wedge E1. And that should be 0. So this whole thing, because I have 2 E1s, this whole thing is going to cancel out and give me 0. So let's see if we can be smart about the multiplications we do and see if we can only write down the ones that are going to matter. Okay? So let's see. Okay. So we don't need that one. So let's just go through systematically. So if I take the first factor, maybe I'll use highlighting. If I take the first factor, there's E1 and E2. Well, if I multiply by E1 or by E2, I'll have a duplication. I'll be multiplying one of them by itself, so I won't need it. So I think the only term I need here is going to be the last one. So E1, E2, and then put an E3 on the right. And now let's move on to our next term. So now I have E2 and E3. Well, I don't want to use those. Those aren't going to be helpful. But I might need that E1. So let's do that. So let's add, let's see, it'd be 18, E2, E3, and then an E1. Remember the order, we go left to right, right? So we're multiplying this E1, it happens on the right. So that will happen there. And now, okay, now we move on to the third term. And again, the only thing we're going to need to multiply it by is this one. So if I put those together, that's going to be negative 8, E1, E3, E2. All right. So now we got a little bit of rearranging to do. Let's try to straighten everything out so that we get everything in the right order. So what I'm going to do is I'm going to swap these two factors. So that's going to introduce a minus sign. And I have E1 in the middle. And then on this one, I'm going to swap these two factors. So I get a plus 8, E1, E2, E3. And now I'm almost done. I just want to do one more swap in this middle one. I'm going to swap the first and the second factor. So now I'm going to get another negative sign. So now I get 18, E1, E2, E3, and this term is the same. And oh my gosh, if I have three common terms. So they're all going to be E1, E2, E3. And now what do I have? Well, I have 23. And let's double check, what was our determinant? It was 23. So this process, which probably feels extremely mysterious to you, like why on earth would we ever do that? Well, someone at one point had a really good reason to try and explore this. And what they did was they discovered that that's what the determinant kind of turns out to be. And so if you like this and you want to compute your determinants this way, that's great. That's wonderful. It's not the fastest way. The fastest way is to kind of row reduce matrices, and we'll do plenty of that as well. But if you want to hear more about this or hear about the applications,